Hello guys, welcome back again. So today's video will be on one-way slab, design of one-way slab, and we will see the design steps. What are the steps to design a one-way slab? And later on in the next video we will see the various checks that we have to provide after designing the slab. So before I start with the problem, let me tell you there are two types of slab. The first one is the one-way slab and the other one is two-way slab. So the slab spanning in one direction is called as one-way slab, while a slab spanning in two directions is called as two-way slab. And in one-way slab, the tension reinforcement is provided only over the shorter span, and in two-way slabs it is provided in both the directions, because in two-way slabs the slab deflects on both the directions. So the basic criteria for determining the type of slab would be depending upon the aspect ratio of the slab, which is given as Ly, which is given as the longer span upon shorter span. So in this case our longer span is 6.2 meters and the shorter span is 3 meter. So it is very obvious that our aspect ratio is 2.067 something. Okay, so if the aspect ratio of the slab is greater than 2, then it is a one-way slab. If it is less than 2, then it is a two-way slab. Okay, so let's start off with the design. So the design a slab of size 3 meter by 6.2 meter for a living room of a residential building. They have given the floor finish as 1.5 kilonewton meter per meter, and use M20 concrete and Fe415 steel. Okay, so the first step would be to determine the depth of the slab. So this will be a trial depth, and if our checks are satisfied, we will use this depth only. So the first step would be to determine the depth of the slab. So this is determined by the span by depth ratio. The formula is D is equal to span upon basic value multiplied by the modification factor. So this is given in clause number 23.2.1 in the IS code. There are various values for the basic values for various types of slab. There is continuous slab, there is simply supported slab, then there is cantilever slab. For cantilever slab it is 7, for simply supported slab it is 20. So ours is a simply supported slab, so we will take the basic value as 20, and the modification factor is assumed somewhere in between 1.2 to 1.5. so our depth would be this span would be the shorter span. The basic value is 20 for simply supported slab, multiplied by the modification factor. So I'll assume the modification factor as 1.5. It comes to around 100 mm. So I'll assume a value greater than 100 mm. I'll assume it as 125 mm. So if I take the size of bar as 10 mm and a clear cover of say 15 mm, so the total depth of the slab would be, total depth equals the effective depth plus half the diameter of the bar, that is 5 mm. For 10 mm bar it would be 5, plus take a suitable clear cover. So 125 plus 5 is 130, say 20 mm. So our total depth would be 150 mm. Okay, this was the calculation of depth. The second step would be to calculate the effective span of the slab. Okay, so this is also given in the IS code. It is given in clause number 22.2. So the IS code says that the effective span would be, out of these two, first one would be the span of the shorter span of the slab plus the effective depth. So our span is 3 meter plus the effective depth is 0.125 meter, that is 3.125. And in the second case it should be the span of the slab plus the size of the end supports. So if we assume that the end supports are of 300 mm, that would be 0.3 meter, and that the total would be 3.3 meter. So out of these two we have to choose the smaller value. So our L effective would be 3.125 meter. So in all the further calculation we will use this value of the effective span. Now the third step would be to calculate the load. So basically there would be two types of load, that is the live load and the other one would be dead load. If any other load is given to you, then you have to also calculate that. So the first one would be the dead load. Dead load is the weight of the slab. So let's assume the density of concrete as 25 multiplied by the depth of the slab, that is 0.15. So we get it as 3.75 kilonewton per meter square. Okay, and the floor finish is given to us as 1.5 kilonewton per meter square, and the live load is not given to us, so we'll just assume a live load. So the live load is, let's say, 4 kilonewton per meter square. So if we add all these up, we will get 9.25 kilonewton per meter square. So this is the total load acting on the slab, but we need the uniformly distributed load that will be calculated as the load per meter. So if we divide it by 1 meter, we will get 9.25 kilonewton per meter. So the next step, once we get the load, the next step would be the calculation of moments. Okay, so now we have the load which is acting on the slab, which was 9.25 kilonewton per meter. So with this we can also calculate the maximum moment the slab is subjected to, which is same as the simply supported beam, WL square by 8. So we'll also multiply this by 1.5 because this load was the working load. So W is 9.25 multiplied by the effective span, that is 3.125, divided by 8 multiplied by 1.5. So the total moment will be 16.93 kilonewton meter. So the next step after this would be to calculate the depth of the slab using bending moment consideration. So the first step would be check for depth. So most of the time your slab would be safe in this check. We will use the formula for singly reinforced beam, 0.36 FCK, XU max B D minus 0.42 XU max, M is 16.93 is equal to 0.36 multiplied by 20, and XU max would be 0.480 because the steel is Fe415, 1000 because we assume as a unit width of the slab, D minus 0.42 into 0.48 D. So everything is given, only the value of D is unknown. If we put all of this on the calculator and solve for D, we will get D as 78 mm, which is less than 125 mm, which we assumed earlier. So your slab is safe in this condition. So after this, the next step would be to calculate the area of tension steel. So again, in this case we'll use the same formula which was for the simply supported beam, that was AST equal to 0.5 FCK upon Fy, 1 minus under root of 1 minus 4.6 m upon FCKB d square multiplied by b into d. And now I'll plug in all the values. 0.5 multiplied by 20 upon 415, 1 minus 6, 16.93 is the moment for unit width of the slab, and the effective depth is 125 mm square. 1000 multiplied by 125. So I get the value of AST as 402.16 mm square. Once you get the area of steel, you can easily calculate the spacing for the individual reinforcements. So the spacing can be calculated by spacing is equal to area of 1 bar upon area required multiplied by 1000. This is the width of the slab, because we have to calculate the spacing per meter width. So the area of 110 mm bar would be pi by 4 multiplied by 10 square upon 402.16 multiplied by 1000. So we get spacing as 195 mm. You can also check for maximum spacing criteria. The maximum spacing is for slab is 3 multiplied by d, or 300 mm. So our spacing which was calculated here should not exceed 3d or 300 mm. This is given in clause number 26.3.3. So in this case our spacing is 195 mm, which is clearly lesser than these two values, so our slab is safe. Okay, so we also have to check for the minimum steel and maximum steel. AST minimum is 0.85 B into D over Fy, so that is 256 mm square, and AST maximum is 0.04 B into capital D, which is the overall depth, that is 6000 mm square, and our calculated values in between these two values, that is 402 mm square. So our slab is satisfying the criteria for minimum and maximum steel. This is given in clause number 26.5.1.1. okay, this is with the actual calculation of steel and the spacing. The next step would be to check for all the data that you have calculated as per the design, and we'll see it in the next video.